Hello everyone, my name is Aditya Tiwari, Assistant Professor, CSVTU, Bhilai. In today's tutorial, we discuss about the recursion in data structure. So, recursion is a powerful technique used in programming, including data structure operations, where a function calls itself during its executions. In the context of data structure, recursion allows us to break down complex problems into simpler self-referential subproblems. Recursion is based on the concept of divide and conquer. It involves solving a problem by breaking it into smaller incidents of the same problem. This is done by eventually reaching a base case where a straightforward solution is available. Each recursive calls works on a smaller subproblem until the base case is reached, and the result are combined to solve the original problem. Now we understand how recursion works. So recursion involves two essential elements for its operation. First, the base case and the recursive case. The base case acts as the stopping condition for the recursion, ensuring that it doesn't continue identifying and offering a solution to the most basic version of the problem. On the other hand, the recursive case determines how the problem is divided and solved in a recursive fashion. When a function encounters a recursive case, it calls itself with a smaller or modified version of the original problem. This recursive calls create a new instance of the function. This recursive calls, or we can say that it continues until the base case is reached, at which point the function returns a value or performs a specific action. The return value from each level of recursion are combined to obtain the final results. It's important to design recursive algorithm carefully, ensuring that the base case and well-defined and the recursive calls approach the base case effectively. Otherwise, the recursion may lead to infinite loop and stack overflow errors, consuming excessive memory resources. Recursion is widely used in data structure operations such as tree traversal, sorting algorithm like quick sort and merge sort, graph traversal, and finding solution to problem like of Tower of Hanoi, the Fibonacci sequence, and many others. Its elegant and intuitive nature makes it a valuable tool in algorithm design, simplifying complex problem into manageable subproblems. Suppose if you conduct any event and you single person handle all the operation, so it is quite difficult to handle that particular operation. So when we conduct any program, any event in a college, so we distribute that program to a multiple student. We make a team one by one, and we distribute the big program, big event into a different section. Like registration committee is different, welcome committee is different, hospitality committee is different. So we make a different committee, and we distribute the big problem into a big event into a sub problem, and distribute our task to the group of students. So easily they can handle the event, and after we merge all the portion of the event and we conduct a successfully event. So basically 5 main recursion methods in data structure, like first one is tail recursion. So tail recursion is a specific form of recursion where the recursive call is the last operation performed in a function. In other words, there is no pending consumption after the recursive call. The characteristic distinguishes tail recursion from other form of recursion. It enables certain optimization in some programming language and compilers. So we can also discuss the advantages of tail recursion, like tail recursion allows for efficient memory utilization. It eliminates the risk of stack overflow and large inputs. Tail recursive functions can be optimized to use a constant amount of memory. Tail recursion enables certain optimization in some programming languages and compilers. So, consideration for tail recursions, like not all programming languages and compilers supports tail call optimization. Tail recursion is only beneficial when the recursive call is the last operation performed in the function. It's important to ensure that the problem can be solved using tail recursion, and that is provides a clear advantage over other approaches. Debugging tail recursive function may be more challenging due to the absence of immediate stack frames. Second, recursion like binary recursion. Binary recursion involves dividing a problem into two smaller subproblems and solving each subproblem separately. The results of the subproblems are then combined to obtain the final solution. This approach is often used when dealing with binary tree structure or problems that can be divided into two distinct parts. Now, use case and consideration of binary. So, binary recursion finds common usage in scenarios that entail binary tree structure, including tree traversal searching and manipulation. It provides a natural and intuitive way to handle problems that exhibit binary-like structure, where each node that at most two child nodes. Binary recursion is often employed in tasks like finding the maximum or minimum value in a binary tree. It is also used in determining the height or depth of a tree, or performing operation like insertion or deletion in a binary search tree. It can also be utilized in binary sorting algorithm like quicksort or binary search. In this algorithm, the problem is divided into two halves in each recursive steps. Consideration when using binary recursion including ensuring that the problem can be effectively divided into two distinct subproblems. In addition, the combination of their solution leads to the desired result. So, next recursion technique is linear recursion. Linear recursion refers to a recursive approach where a problem is divided into a single subproblem. Each recursive call reduces the problem size by a constant factor until a base case is reached. When terminates the recursion, linear recursion is often and when solving problem that can be broken down into smaller similar instances. So, when we comparison with other recursion methods, linear recursion is a comparatively uncomplicated and easily comprehensible method when contrasted and other recursion techniques. It provides specifically advantages when the problem at hand can be simplified to a solitary subproblems. For example, computing the Fibonacci sequence or determining the factorial of a given number. Nevertheless, it is important to acknowledge that linear recursion may exhibit greater time complexity than alternative approaches. It is due to its tendency to involve repetitive computations. Now, next recursion technique is mutual recursion. Mutual recursion is a form of recursion where two or more functions calls each other in a cyclic manner. These functions work together to solve a problem by dividing it into subproblems. which are then solved using the corresponding manually recursive functions. So benefits of mutual recursions are provides a modular and organized approaches to problem solving, allows functions to divide the work among themselves leading to more manageable code, enable a clear separation of responsibilities and promotes code's reuse, solve problems that involve complex dependencies and interrelated computations, facilitates the implementation of algorithms that require alternating steps or coordination between functions. Potential challenges of mutual recursion like requires careful design and coordination between the mutually recursive function to avoid infinite recursion. Debugging and understanding the flow of execution can be more complex, may result in increased memory consumption and runtime overhead due to multiple function calls. Requires are though understanding of termination, condition and dependencies between functions. Inefficient implementation or incorrect termination conditions can lead to poor performance or incorrect results. Last one is nested recursion. Nested recursion occurs when a recursive function calls itself with the recursive call as one of its arguments. In other words, the input parameter of the recursive call is the result of another recursive call. Advantages of nested recursion are it has the ability to solve problems with complex dependencies relationship. It offers a versatile and allocate approach to managing numerous recursive innovation. It enables the decomposition of problems into smaller instances even with intricate patterns. It can be used to solve problems that can be easily tackled using other recursion methods. So, consideration for nested recursion are it may result in exponential time complexity for certain problem instances. Careful design is necessary to avoid infinite recursion and ensure termination. It requires an understanding of the problem's recursive structure to utilize nested recursion effectively. Performance consideration should be taken into account, especially for large inputs. Now we come on the recursive algorithm. So what is a recursive algorithm? A recursive algorithm is an algorithm approach that solves a problem by breaking it down into a smaller subproblems of the same kind. It uses the concept of recursion where a function calls itself to solve these subproblems iteratively. Each recursive calls reduces the problem size until a base case is reached. When provides a terminating condition for the recursion. By solving the subproblems and combining their solutions, the recursive algorithm eventually arrives at the solution to the original problem. So, recursive algorithm offers a powerful and elegant way to solve complex problems by decomposing them into a simpler, self-referential subproblems. They are particularly useful when the problem exhibits a recursive structure or can be divided into smaller instances of the same problem. However, it's important to design recursive algorithm carefully considering termination, conditions, base case and performance implementations to ensure correctness and efficiency. So, type of recursions. Recursions in the data structure can be classified into different types based on the way functions call themselves. Two main important types of recursion are direct recursion and indirect recursion. Let's we understand one by one what are that one. The first one is a direct recursion. Direct recursion is a type of recursion in which a function directly calls itself during its execution. The function solves a smaller subproblem and then calls itself with the reduced subproblem until it reaches a base case that terminates the recursion. Direct recursion involves a straightforward and explicit self-reference within the function body. Also, we discussed the pros and cons of direct recursion. Direct recursion offers some advantages in problem solving and algorithm design. Simplicity, the main advantages of the direct recursion, like direct recursion often provides a straightforward and intuitive solutions for problems that exhibit self-similar subproblem. Another one is readability. Recursive function can often express the problem solving logic more clearly and consciously, making the code easier to understand. Direct recursion has some drawbacks also, like memory usage. Like recursive function calls consume memory as each call creates a new stack frames. If the recursion depth is large, it may lead to stack overflow errors. Another drawback is performance overhead. Recursive calls involves functions called overhead, which can impact performance compared to interactive approaches. Next is tail recursion optimization. Direct recursion may not benefit from tail recursion optimization, where the recursive call is the last operation in the function. This optimization eliminates the need for maintaining multiple stack frames, enhancing performance. So, these are the drawbacks of direct recursion. Now, we discuss about the other type of recursion, that is a indirect recursion. So, indirect recursion is a type of recursion in which a function calls another functions. The chain of function calls leads back to the original functions, creating a cycle. Indirect recursion, there is a circular dependency among multiple functions, where each function calls another functions in a sequence until the base case is reached. So, now we discuss pros and cons of indirect recursion. So, indirect recursion offers certain advantages and disadvantages also. So, the problem decomposition is the advantages, or we can say the pros of the indirect recursion. Indirect recursion can be used for breaking down a complex problem into a smaller independent subproblems. Each function focuses on solving a specific part of the problem. Another advantage is like code modularity. By dividing the problem solving logic across multiple functions, the code can be organized and modularized, improving readability and maintainability. There are few drawbacks of this indirect recursion, and they are: first one is the complexity. Indirect recursion can introduce additional complexity due to the interdependencies between functions. This complexity can make code harder to understand and debug. Another drawback is execution order. The execution order of function is indirect recursions is crucial. Indirect sequencing or missing base case can lead to infinite loop or incorrect results. Performance overhead. Similar to direct recursion, indirect recursion can incur function called overhead and memory consumptions. Care must be taken to avoid excessive recursive calls. Direct recursion involves a function calling itself directly, while indirect recursion involves a chain of function calls leading back to the original functions. Both types have their advantages and disadvantages, and their suitability depends on the problem at hand. Understanding this type of recursion can help in designing efficient and elegant recursive algorithm while considering the potential threats of. Now we understand how to use recursion. The best example of recursion is the Tower of Hanoi problem. As we played in the childhood time, Tower of Hanoi problem, you also played, guys. So today we discuss Tower of Hanoi problem under the how we use in a recursion in data structure. So it is a classic problem where you try to move all the disk from one page to another page using only 3 pages. Initially, all of the disks and stacked on top of each other with the larger disk under the smaller disk. You may move the disk to any of 3 pages as you attempt to reallocate to all of the disk. But you cannot place the larger disk over smaller disk and only one disk can be transferred at a time. This problem can be easily solved by divide and conquer algorithm. By this example, you can understand. Here we having a 3 disk on page A. Then we having a 3 pages like A, B, and C. You also called a stand A, B, and C. Right now, in a stand, all the 3 disks are available, larger than next to the larger and the smaller one. We have to shift all the disks one by one. We can pick one disk at a one time, and we can fix that the particular disk at any stand B or C. But the condition is that you have to fix a larger disk at the bottom case, the bottom of the surface. Then you fix the next to the larger above that particular disk. So one by one we can shift the disk, like the smaller disk. First we shift on the C stand, or we can say C page. Then we shift next to the larger disk on the B page or B stand. Then again back pick the smaller disk from the C page and back to the B page. Then we move the larger disk from A disk to the last C page. Then we pick the smaller disk from page B, then back to the stand A, or we can say page A. Then we pick second larger disk from B and insert into a C stand or C page. Now in a C stand, having a two disks are fixed, the larger one and next to the larger one. Next we pick the smaller disk from the first page, from A page, and insert at the stand C or the page numbers page C. Now all disks are shifted one by one in this sequence from A page to the C page. The sequence are one by one we can shift, and the motto is that finally the larger disk, all the disks are fixed in the same sequence where from the pick from the page A to the page C. So with the help of B, we can shift all 3 disks one by one into a C. So in the above 7 steps, all the disks from page A will be transferred to C. Like only one disk will be shifted at a time. The smaller disk can be placed on a larger disk. Let T of n be the total time taken to move n disks from page A to page C. Moving n minus 1 disks from the first page to the second page, this can be done in T of n minus 1 steps. Moving larger disk from the first page to the third page will require first one step. Recursively, moving n minus 1 disk from the second page to the third page will require again T of n minus 1 steps. So the total time taken is T of n equal to T of n minus 1 plus 1 plus T of n minus 1. We can write 2 of T n minus 1 plus 1. So the best practice and common pitfalls, like when using recursion in C, it's essential to follow some best practices to ensure a correct and efficient implementation. Identifying the base case carefully. Base case provides the termination condition for recursion. Ensure that the base case condition is well defined and reachable to avoid infinite recursions. Another one, ensure progress towards the base case. In the recursive case, ensures that the problem is being divided into smaller subproblems that leads to reaching the base case eventually. Each recursive call should make progress towards the base case. Another one, properly manage memory and resources. Recursion may consume a significant amount of memory, especially if the recursive calls are nested deeply. Be mindful of memory uses of consider optimization techniques like tail recursion or memorization when applicable. Test with different input size. Recursion may have different performance characteristics depending on the input size. Test your recursive function with various input size to identify any potential performance bottlenecks. Now we discuss common pitfalls to avoid when using recursion in C include like stack overflow. If the recursion depth becomes too large, it can result in a stack overflow errors. This happens when the call stack, which keep track of function calls, exceeds its memory limit. Ensure that your recursive function terminates within responsible recursion depth to avoid this issue. Redundant or incorrect recursive call is another one. Be careful with the recursive function calls within the function body. Make sure that the arguments passed to the recursive call are appropriate and lead to a valid progression towards the base case. Incorrect and redundant recursive calls can lead to incorrect result in finite recursion. Using recursion in C. Recursion in C follows a similar concepts as in C++. Let's explore the syntax and basic implementation in C along with its limitations and considerations. Syntax and basic implementation. So, in a C is also based on defining the function that calls itself. Here, the general syntax for the recursive function in C like also we can say the structure of the recursive function bears resembles to that of C++ and composing both the base case and the recursive cases. By this we understand like return type function name, you can pass any parameter. After that, that's particular base case termination condition, you can pass that one. If base case condition is true, then go for the return the base case value, you can insert the value, then go close the structure. Then recursive case, dividing the problem into the smaller subproblem, it means the call the function recursively. Then you write the return recursive function call and you pass the arguments. So, end of the structure, by this we can divide the problem into a subproblem. So, limitation and considerations. When using recursion in C, there are a few limitations and consideration to keep in mind. Lacks of automatic memory management. C does not provide automatic memory management like C++. Therefore, you need to manage the memory allocation and deallocation manually, specifically when dealing with dynamically allocated memory inside a recursive function. Limited recursion depth. C compiler often have a limited recursion depth due to stack size restrictions. If the recursion depth exceeds the limit, it can lead to a stack overflow errors. Be cautioned when implementing recursion in C and consider optimizing the code and using an iterative approach for deep recursions. Another one is efficiency corners. Recursion in C can be less efficient than in iterations in creation scenarios. Each recursion call anchor function calls overhead and may lead to redundant calculations. Consider the problem characteristics and analyze the performance implications before deciding to use recursions. Use case of and performance considerations like recursion in JavaScript find the application in various scenarios as follows, like trees and graph traversal. Recursive algorithm and commonly used for traversing tree like graph like data in data structure. For example, recursive traversing a binary tree for or finding path in a graph. Sorting and searching, another technique. Recursive algorithm like merge sort or the binary search can be implemented in all the languages efficiently. Sort for each search through data. When using a recursion in any language, to consider performance implementation due to any C, Java, threaded nature and event driven environment. So excessiveness recursion can be lead to blocking the event loop, causing unresponsiveness like that. Carefully optimization the code and consider tail recursion or the interactive approaches when applicable to improve performance. So functions performing benefits like lots of emulative data structure and higher order functions like Scala encourage the user of the immutable data structure when are all suited for recursion. Immutable data avoids side effects and make it easier to reason about code correctness. In higher order functions, Scala like higher order functions enable the composition and combination of recursive functions. You can use higher order function like map, filter or to fold or apply recursion to collection or performance complex operations. So the difference between recursion and iteration. Recursion and iteration are two distinct approaches to problem solving and algorithm design. While both methods involve repetitions, they differ in their execution and the underlying mechanism they utilize. The following table highlights the key differences between recursion and iterations. Like in recursion, a technique where a function calls itself during the execution, but in iteration, the process of repeating a set of instructions in a loop. In recursion, involves dividing a problem into a smaller instance of the same problem. In iteration, repeats a block of code until a specified condition is met. In recursion, typically used for solving problems with a recursive nature such as tree traversal or finding factorial. And the iteration suitable for tasks that requires repetitive execution like searching or sorting. In requires a base case of terminates the recursion. In iteration requires a loop condition to control the repetition. In recursion can be more conscious and intuitive or creation problems. In this one, often more straightforward and easier to understand. And recursion may requires more memory due to the function called stack. Iteration generally consumes less memory. In recursion can be less efficient in terms of time complexity for same problem, for some problems. In iteration often more efficient in terms of the time complexity. And the last one, in recursion may result is deeper level of the code nesting, and this one keep code structure flatter and simpler. So use case of recursion and iteration like that one. Recursion is often used in the following scenarios like tree traversal, graph traversal, finding permutation and combination, solving problem with the divide and conquer approach, and the last one is the parsing and evaluating expressions. Iteration is commonly employed in the following situation like searching algorithm, sorting algorithm, numerical computations, input validations and processing, and handling repetitive tasks efficiently. Analysis of the recursion. One may argue why to use recursion as the same task can be done with iteration. The first reason is to recursion makes a program more readable, and because of latest enhanced CPU system, recursion is more efficient than iteration. Then time complexity. In the case of iteration, we take number of iteration to count the time complexity. Likewise, in case of recursion, assuming everything is constant, we try to figure out the number of times of recursive calls is being mode. A call mode to be a function is O of 1, hence the n number of times a recursive call is made make the recursive function of O of n. So, the space complexity is counted as what amount of extra space is required for a module to execute. In case of iteration, the compiler hardly requires any extra space. The compiler keeps the updating the value of variables and variable used in the iterations, but in the case of recursion, the system needs to store activation record each time a recursive call is made. Hence, it is considered the space complexity of recursive function may go higher than that of function with iteration. So, finally, conclusion, recursion is a fundamental concept in the data structure that empowers programmers to solve complex problems using an elegant and intuitive approach. By understanding the intricacies of recursion, the various methods and types, and its practical implementation in different programming languages, you can become a more proficient problem solver and algorithm designer. However, it is crucial to consider the drawback and performance implementation of recursion to make informed decision in real world scenario. With this knowledge, you can harness the power of recursion to write efficient and elegant code in your data structure environments. So for this tutorial, thank you.